Banach lattice theory has long been a cornerstone of functional analysis, offering a framework that seamlessly blends order structures with topological properties. The study of Banach lattices is essential for understanding various areas of mathematics, including operator theory, spectral theory, and measure theory. Peter Meyer-Nieberg's Banach lattices provides an extensive exploration into this rich field, focusing on the fundamental aspects of Rie's spaces and their applications to classical and contemporary problems in functional analysis. The book delves deep into topics such as order convergence, Banach lattice properties, spectral theory, and even touches upon advanced concepts like Grothendieck spaces and the Rodin-Nikodym property. By presenting both classical results and recent advances, Nieberg aims to offer a comprehensive guide that bridges foundational knowledge with cutting-edge research. The significance of this book lies in its accessibility for advanced undergraduate students, as well as graduate students and researchers who are new to the field. The clarity of presentation and the inclusion of numerous exercises make it an excellent resource for self-study or coursework, while its depth ensures it will be valuable for seasoned mathematicians seeking a deeper understanding of Banach lattices. In the first part of his work, Peter Meyer-Nieberg introduces readers to the core concepts of Banach lattice theory by exploring the intrinsic structure of Rie's spaces. He begins with the definition and properties of Rie spaces, normed Rie spaces, and order convergence. This foundational material provides a solid grounding in the basic terminology and techniques needed for further study. Nieberg emphasizes the importance of understanding Rie spaces through their constituent parts: bands, ideals, and sublattices. A band is a closed ideal that contains all its order limits, while an ideal is a special subset where any element can be approximated by another within it. Sublattices are similar, but without necessarily being closed under the lattice operations. Understanding these components allows for a more nuanced analysis of Banach lattices. One key aspect discussed in this chapter is the role of regular operators and order-bounded functionals, which are crucial tools in functional analysis. Regular operators are linear maps that preserve the structure of Rie spaces, while order-bounded functionals ensure that certain properties hold under boundedness constraints. These concepts form the backbone for more advanced topics covered later in the book. Nieberg's approach is particularly engaging because it not only presents these foundational ideas, but also highlights their practical applications through numerous examples and exercises. By starting with clear definitions and progressing logically to more complex theories, he helps readers build a robust framework of knowledge about Banach lattices from the ground up.
In this section, Nieberg examines classical Banach lattices and their properties, drawing on foundational results originally demonstrated for specific spaces. He begins by characterizing Dedekind complete KK Kalkin spaces, focusing particularly on ideals and bands within these structures. These concepts are essential in understanding the behavior of operators acting between different types of Banach lattices. A significant portion of this chapter is dedicated to the representation theorem for M spaces with a unit. This theorem provides insight into how certain Banach lattices can be represented as subspaces of larger spaces, offering valuable tools for solving problems within these domains. By analyzing these representations, Nieberg illustrates how seemingly abstract concepts become more tangible and applicable. Moreover, the discussion on order-bounded sets reveals their importance in establishing key results throughout the book. Order-bounded sets are those whose elements lie between two specified points of a lattice, ensuring that they remain contained even under certain transformations or operations. The author stresses that these sets play pivotal roles in various proofs and theorems, including those concerning spectral properties of operators. The inclusion of detailed examples throughout this chapter enriches the reader's comprehension by illustrating how abstract theories can be applied practically. These applications range from simple illustrative cases to more complex scenarios involving advanced mathematical constructs. As a result, readers gain not only theoretical knowledge, but also hands-on experience in problem-solving within Banach lattice theory. The third chapter shifts focus towards operators defined on or with values in Rie's spaces. Here, Nieberg explores various types of operators and their interactions within these mathematical structures. A central theme here is the study of regular operators, linear maps that preserve positivity and other lattice properties, and how they behave under different conditions. Lattice homomorphisms are another important focus area. These are functions between Rie's spaces that respect both the algebraic structure and order relationships. Nieberg explains their significance in maintaining the integrity of Banach lattices when subjected to transformations or mappings. He also discusses order-weakly compact operators, which generalize classical notions of compactness for operators on Banach spaces. The spectral properties of positive operators on complex Banach lattices are explored in depth. Positive operators have non-negative eigenvalues and play a crucial role in understanding the behavior of systems described by these operators. Nieberg presents Freudenthal's spectral theorem as an essential tool for approximating elements using step functions, demonstrating how this theorem provides insights into spectral decomposition. Throughout this chapter, examples are used extensively to reinforce theoretical concepts with practical illustrations. These applications span from simple demonstrations of basic principles to intricate analyses involving sophisticated mathematical constructs. By providing both intuitive explanations and rigorous proofs, Nieberg ensures that readers grasp the nuances of operators on Rie's spaces comprehensively. The fourth chapter delves into the Banach space properties exhibited by Banach lattices. Key topics include property U for Banach lattices, subspaces of Banach lattices, and embeddings of C and CA, spaces of continuous functions, into these structures. Nieberg investigates conditions under which a Banach lattice possesses property U, a characteristic indicating certain desirable compactness properties. He also explores the implications of having subspaces that resemble classical spaces like C or KIA. These investigations highlight how Banach lattices can exhibit behaviors similar to those observed in traditional Banach spaces while maintaining their unique lattice structures. An important aspect covered is embedding results, particularly regarding the inclusion of certain function spaces into Banach lattices. Such embeddings allow researchers to leverage established results from functional analysis when studying more specialized settings like Banach lattices. By examining these mappings, Nieberg demonstrates how broader theories can inform specific instances within this area. Throughout this chapter, Nieberg weaves together theoretical developments with practical examples, illustrating both the elegance of Banach lattice theory and its utility across diverse mathematical domains. This combination fosters deeper appreciation for the interconnectedness between different branches of mathematics, while emphasizing the importance of understanding fundamental principles before diving into advanced applications. The final chapter of Banach lattices addresses advanced topics including Grothendieck spaces and the Radon-Nikodym property. Here, Nieberg discusses characterizations involving separable-order Denable Banach lattices due to Gossab and Talleyrand. These results offer profound insights into the structure of these spaces and their relationship with more familiar Banach space properties. The discussion on essential spectral radius for operators on Banach lattices introduces another layer of complexity, extending classical spectral theory beyond Hilbert spaces to encompass a wider class of vector spaces equipped with order structures. This extension is particularly relevant, given that many physical phenomena are naturally modeled using Banach lattices rather than simple Hilbert spaces. By exploring these advanced concepts, Nieberg bridges the gap between theoretical foundations and real-world applications, encouraging readers to consider how abstract mathematics can be applied in practical context. The inclusion of these sophisticated topics ensures that even experienced mathematicians will find value in this comprehensive treatment of Banach lattice theory.
In conclusion, Peter Meyer Nieberg's Banach lattices serves as an invaluable resource for anyone seeking a thorough understanding of this rich and versatile area of mathematics. By covering both foundational concepts and advanced topics, the book provides readers with a comprehensive overview that bridges theoretical knowledge with practical applications. Whether you are a beginner looking to establish a strong foundation, or an experienced mathematician hoping to expand your expertise, Banach Lattices offers valuable insights into this vital field in modern mathematics.